two variables are said to be co-integrated if the error term from their linear regression model is I1. In other words, in the equation that we have in the first line over there, that's the linear regression between yt and xt. Y is the dependent variable, xt is the independent variable. Both of them can be non-stationary. But if the residual from this linear regression model is stationary, is I1, we will say yt and xt are co-integrated. That basically means those two have a similar stochastic trend. And since the difference ET is stationary, they never diverge too far from each other. In practice, this is a very useful property. That means, okay, yt and xt on their own, we don't know where they're going to go because they could be random walk. They can be non-stationary. So they just wander around. However, we investigate the pattern, at least within the sampling period. The difference between those two, or the gap between those two, which is captured by this linear regression model, or ET, remains stable. So they never wandered too far away from each other. The relationship is stable. Then we can make use of this long-term stable relationship in linear regression analysis. In this case, the regression analysis is valid. We do not have to have concern about the spurious regression. The regression itself as a whole is stable. And we need to test for stationarity of the residual instead of on the variables themselves. We don't worry about the stationarity of yt or xt. We look at ET only, whether ET is stationary or not. If it is I1, then we will see those two variables are co-integrated. And I also would like to point out that because of this type of test, the critical values will not be the same as the one that we introduced before. Because the previous one is unit root test on the variables themselves. This one is a unit root test, but it's on the residual of a regression model. So we have three sets of critical values, and they change based on the specification of your regression model. So if the regression model does not contain an ecosum, which is the first one, or does not contain a intercept term, that's the first one, you are going to use the first set of critical values. If there is an intercept term, which is B1 over there, that's the second set of critical values that should be used. And lastly, if you have a time trend included in your regression model, then you need to use the third set of critical value. So if we even have a look at the significance values or critical values on the slide, and we'll go back a couple of slides to this slide. That's the critical values used at a typical unit root test, and they are quite different from each other. The good news is in practice, we always use the software to perform these tests. So as long as you use the correct command, the software will pick the correct critical values for you. Now let's use this federal bound rates and the 3 years bound rates as example to perform a co-integration test. So we have already found out that both variables are not stationary. So we are not using the first difference variables here. Those are the level variable, the original one. And we run regression model by using BT as the dependent variable and FT as the independent variable. R squared is quite good. It's over 80%, close to 90%. And the variable, the coefficients are significant. However, it potentially has spurious regression problem. Both variables are not stationary. But we can perform a unit root test for stationarity in the estimated residuals. So we test the residuals instead of those two variables. We know they are not stationary. The residuals, we run this regression model, and but we're following the procedure we introduced before, the test statistics minus 4.196. Then the critical value, the corresponding critical value, because the regression model contains an intercept term, but no trend. So the critical value is minus 3.37. So that's the critical value. And we come back to this slide and we can compare, okay, this test statistics is obviously in the rejection region, and we can reject the null hypothesis and conclude the residual series is I null, and the regression result are valid 2-time series, or BT and FT are co-integrated. The next important concept to introduce is error correction model. So if we consider an autoregressive distributed lag model, ARDL model, with non-stationary variables like this one, in other words, both y, t, and xt are not stationary. However, if yt and xt are co-integrated, that basically means there is a long-run stability or stable relationship between them. And we actually can make use of that property to estimate this regression model. So to derive this long-term relationship, we have to look long-term. So in the long run, all the value of y's will be the same, that's y. All the values of xt will be the same, that's x. So time doesn't matter. In the long run, that's one value. And we can get rid of the random error term as well. So we simplified this equation by getting rid of all the subscripts. In the long run, time doesn't matter, and get rid of the random shock. Those are only temporary. And then we can derive the linear relationship in this way. So that's written in the last line. Okay, and then we can rearrange our ARDL model by adding minus yt minus 1 on both sides. So left-hand side, you will have a delta yt. That's the first difference of yt. Why do we want to do that? Because we have already discussed the benefit of taking the first difference. It can change a non-stationary variable to be a stationary one. So that's the purpose of adding this minus yt minus 1 on both sides. So left-hand side, yt is transformed into delta yt, which is stationary. Right-hand side, we need to do a little bit more. So the next step is to add minus delta naught xt minus 1, then plus delta naught xt minus 1 to the right-hand side. That doesn't change anything because this term is 0. However, if we split them into the two terms into the right-hand side, that gives us, okay? So that's the first part is delta xt. That's stationary. The second part is simply just xt. But if we move this part along with yt and we rearrange them, then that gives us a new model like this. So here, beta 1 simply equals to delta over theta 1 minus 1. We just use beta 1 to denote it. And the theta 1 minus 1 becomes minus alpha. That's just a notation. But this equation has something that is very nice because every single one of them is stationary. So the first one, left-hand side, is the first difference of yt is I null. And the first term in the right-hand side, you may notice that, that within this set of brackets, that's the error term from the linear regression model from the long run. And if yt and xt are co-integrated, the whole thing within this set of brackets is stationary. Then if we move to the last part, delta xt is the first difference of xt is stationary as well. If every single one of them is stationary, we can run a linear regression model and it's valid. So this is called an error correction model. Error means within the set of brackets, that's the error term from this linear regression model. And correction basically means this alpha is called error correction parameter. That parameter tells us the rate of adjustment of the series to go back its long-term equilibrium. Okay, so let's use one example to demonstrate how to estimate this error correction model. We still use ft and bt. Both of them are not stationary, but we verify that they are co-integrated. So we estimate an error correction model by using the first difference of bt and ft. Both of them are stationary. And this error term from the linear regression model using bt and ft. So this whole term is stationary. And we can check whether the error term et minus 1 hat equals to the term within there. And we can test whether it's stationary or not. Recall that the critical value of this test is minus 3.37 because we have an intercept term in the linear regression model. And if we go back to this test, you may notice that the test statistics is smaller than the critical values in the rejection region. And we reject the null hypothesis and then conclude they are indeed co-integrated. And this is a valid error correction model. So an error correction model captures two types of relationship, long-term and short-term relationships. The short-term relationships are captured by those first difference. That means, okay, when F changed by F's short-term change or 1 year change, year-on-year change, changed by that much, what is the changes, short-term change in BT will be? So it's captured by 0.842. It's positive relationship. In the long run, we do have a long-term relationship. So BT and FD are positively correlated because if we move those to the right-hand side, you may notice that it should be BT equals 1.429 plus 0.777 times FT. So that's the long-term relationship. And this error term is just the temporary deviation from the long-term equilibrium. And this minus 0.142 is the adjustment rate, is the error correction. How much the process can correct every period and move the time series towards the long-term equilibrium, the long-term relationship. So that's the meaning of a error correction model and why it is so useful, why it is so widely applied in real-life problems. Sometimes, even if we tried very hard, we still cannot establish stationarity for the error term, which means two variables are not stationary on themselves and they are not co-integrated either. In that case, we need to make some transformation to make sure the transformed variables are stationary so that we can use them in linear regression analysis. The technique basically depends on whether the variables are difference stationary or trend stationary. If a time series is difference stationary, that means if we take the first difference, it becomes I1 or I0, becomes I0 or stationary. If it is trend stationary, the equation or the stochastic process usually looks like this. So we can take out a trend and make it stationary. And the procedure is usually, we call it detrending. We just need to take away the trend. So those are two ways of making the variables stationary. Those are techniques that could be used, but there's no guarantee. It will always transform. It can always transform a series from non-stationary to stationary. So let's summarize. If variables are stationary, or I1 and integrated, we can estimate the regression relationship between the levels of those variables without fear of encountering a spurious regression problem. In other words, if variables are stationary on their own, we just use them straight away without any transformation. However, if they are not stationary but I1 and they are co-integrated, we can estimate an error correction model as we have just discussed before. The next case is the variables are I1, which means they are not stationary, but they are not co-integrated either. They failed the co-integration test. In that case, we can only use the first difference of those variables to establish the relationship. And we can build a model with them without a constant term. If the variables are trend stationary, we can either detrend the series by using the formula on the previous slide, or we just put that trend in the regression model directly. That will help us to capture the trend and make the result valid. So those are different situations and the strategy to handle different type of variables.